Hello, Chem 1B. This is Chapter 21, Lecture Video 2, and we're going to be talking about structural isomers. So let's talk about butane first. Butane is C4H10, and it has two structural isomers. This means we can draw two different compounds containing four single-bonded carbons that are different from each other. So here's 5 different compounds, but they're actually not all different. This is what we call the normal chain butane, and it's because it's all attached in a chain. Now, just because we drew it this way doesn't mean we can't draw it other ways. So there's actually only 2 different compounds out of this set of 5 pictures, and it's important to be able to determine if 2 structures that are drawn differently are in fact different. So if we look at this first element, we have a carbon bonded to another carbon, bonded to another carbon, bonded to another carbon in a row. Here we have a carbon bonded to one carbon, bonded to another carbon, bonded to another carbon. So these two are actually the exact same structure and are no different from each other. The same thing is true here. Carbon attached to carbon, attached to carbon, attached to carbon in a row, 4 in a row. Same as this one and same as that one. Here we have a weird angle, but it's still a carbon directly bonded to one carbon, which is then bonded to another carbon, which is finally bonded to the 4th carbon. Again, this one is the same as all of those. It's only when we get to this compound that we actually have a structural difference. Because if you look, now there's only 3 carbons that are actually attached to each other in a row. And this middle carbon has a second carbon attached to it. All the rest are 4 carbons in a row in a chain. But this compound is not, and yet it still is C4H10. So we really only have 2 structures here out of this group of 5 pictures that are actually different. And so we have this structure, this is one structural isomer, and then technically all 4 of these are the same structure, just drawn different ways. So it's very important to be able to kind of distinguish between these. Okay, so let's do some practice with structural formulas as well as skeleton formula. That's what I'm going to use primarily, and isomers. So I know heptane's formula is C7H16. And I also know there are 9 different structural isomers present for heptane. Now the first one, I'm just going to write the straight chain. That's 5, 6, 7, with all the hydrogens shown, and then I'm not going to use hydrogens or carbons anymore. I'm going to use the skeleton formula that you need to kind of start getting a handle on. Now, how we can count these or draw different ones is basically just a matter of changing certain aspects, right? So this is one of my possible structures. A second one, if I'm going to use skeleton formula, I'm going to draw lines. So there's 2 carbons, 1, 2, 3, 4, 5, and I'm going to stop at 6. Because at this point, if I add another one to this chain, I'll get just this structure again. But if I take that last carbon and I put it out here, this still gives me 7 carbons, right, with the circles. We generally wouldn't use all those little circles, so if we finish this structure correctly, it'd be 1, 2, 3, 4, 5, 6, 7. Now, there are 7 carbons and 16 hydrogens still, and this is another structure. Now, I could draw a third one where I do the same thing, 1, 2, 3, 4, 5, 6, but I don't put the carbon here, I put it here. And this is my third structural isomer. Now, if you did something like this, 1, 2, 3, 4, 5, 6, If you're like, okay, well then I'll just put the one over here. These two are identical. Just rotate this around and you get that structure. So you can't do that anymore. So like kind of your space, like three-dimensional imaging, or your ability to kind of look at these and orient them in space in your head, is very useful in this type of problem. So that last one wasn't one. Now what I need to do is I need to stop doing a chain length of 6 like I have for the last two and do a chain length of 5. So 1, 2, 3, 4, 5. Now I have 2 more carbons that I can put on here. I could do one here and one there. And this is a new structure, one that I haven't drawn yet. I can do a 5th one with also a chain length of 5. But this time I could put them both on the same one, like there. I could do a 6th structure, again with a chain length of 5. But this time I could put them both in the middle. And that's different. I could do a chain length of 7, or sorry, number 7. I could do still 5, right? But now I could do one here and one there. That's different from all the 5 ones. I could do 8 still with my 5 chain. Now I could do it like this, 1, 2. This still gives me 7 total. The last structural isomer is going to be cutting it down to a chain length of 4 and putting something together like this. So these are all the 9 isomers of heptane. There aren't any more. If you drew something additionally to anything I drew, then it's odd and you probably are drawing a structure twice without realizing it. So double check, try it yourself, and see what you can come up with. So isomerism and optical isomerism, we've talked a little bit about this in chapter 24. Stereoisomers are things that have the same connectivity but different spatial arrangement. And we don't really have Fach and Mer like we did with coordination compounds. We only have cis-trans in organic compounds. And cis-trans only occurs when there is a double bond. Optical isomers, same as in chapter 24, are when we have 2 non-superimposable images of one another. We call these in organic chemistry enantiomers. Any molecule that exhibits optical isomerism is what we call chiral. A chiral carbon is any carbon with 4 different substituents. Substituents are the things attached to that carbon. So if we look at like methane, methane is not chiral because we have 4 hydrogens. All of them are the same thing attached to the carbon. But if I change these hydrogens to other things, right? If I had a hydrogen there, an oxygen here, maybe a CH3 here, and then maybe a C2H6 there, or H5, C2H5 here. Well, hey, this is different from this, which is different from this, which is different from that. This is a chiral carbon because the groups around it are all different from each other. Enantiomers differ from each other in 2 major ways. All right, so if you have optical isomerism, they rotate polar light differently. And their chemical behavior in a chiral environment where their shape is very, very important, then their chemical behavior will change. So for instance, if you have like an enzyme, enzymes often only fit one optical isomer. So there are a lot of biological things that this can drive. All right, so that should be it. If you guys have any questions, please let me know. Office hours, email, what have you.